In section 2.5, we'll be discussing limits involving infinity. In this section, we're going to investigate the global behavior of functions, and in particular, when their graphs approach asymptotes, vertical or horizontal. Now, if you look at this example here, it says infinite limits. So in example 8, back in section 2.2, we concluded the fact that the limit as x approaches 0 of 1 over x squared does not exist. And you can see what happens with the graph here. Now, by observing the graph, you can see that the values of 1 over x squared can be made arbitrarily large by taking x close enough to 0. Okay, so these values of the function do not approach a number. So therefore, the limit as x approaches 0 of 1 over x squared does not exist. Now, to indicate this kind of behavior, we're going to use the following notation. In general, we're going to write it symbolically, and we're going to say that the limit as x approaches a of the function is equal to infinity. Now, this does not mean that we are regarding infinity as a number, nor does it mean that the limit exists. It simply expresses the particular way in which the limit does not exist. So 1 over x squared can be made as large as we like by taking x close enough to 0. Okay, so again, this limit is going to indicate the values of f of x become larger and larger or increase without bound as x approaches a. Okay, now our first definition, okay, is to state that the limit of a function as x approaches a is equal to infinity means that the values of the function can be made arbitrarily large or as large as we please by taking x sufficiently close to a on either side of a, but not equal to a. Now, another notation form for the limit as x approaches a of f of x is equal to infinity is the following. As f of x approaches infinity as x approaches a. And again, the symbol is not a number, but the expression is often read as the following. It could be the limit of the function as x approaches a is infinity, or we can say that the function f of x becomes infinite as x approaches a, or we can say that f of x increases without bound as x approaches a. Now, similarly, okay, if we take a look at this figure here, you can see that the limit as x approaches a of f of x is equal to negative infinity means that the values of f of x are as large negative as we like for all values of x that are sufficiently close to a but not equal to a. So if you take a look at figure 2 here, okay, you can see that on the function on the left side, the function is eventually approaching positive infinity. Okay, here's the vertical asymptote. Same thing on this side. On the right side, as it approaches a, it's approaching positive infinity. Now, if you look at figure 3, okay, what you notice is we have a vertical asymptote at x equals a, and on the left side, if we follow the function, it's going to be approaching negative infinity down here, and the same thing over here. So I'm going to just indicate that with arrows. Okay, so you can see here that this function, okay, is approaching positive infinity. Okay, whereas this function, okay, is approaching negative infinity. So there is another set of definitions. Now, we can take a look at these similar definitions for one-sided infinite limits. Okay, so as the limit of a function, okay, as x approaches a from the left, okay, that means that if you look at this function here, it's approaching positive infinity. Okay, the second one in b, it's approaching a from the right, and that's approaching positive infinity. Now over here, as x approaches a from the left, it's approaching negative infinity. And as this one is approaching a on the right, it's approaching negative infinity. So the line x equals a in all 4 scenarios is called a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. Okay, so you have the limit as x approaches a is infinity, whereas if it approaches a from the left and from the right, it's approaching positive infinity. As the limit as the function approaches a is approaching negative infinity, then as x approaches a on the left and on the right, it's approaching negative infinity. Okay, so let's take a look at example number 1. Okay, so in example number 1, we want to be able to evaluate one-sided limits and finding the one-sided infinite limits. Okay, so if we take a look at the first one, okay, what it's saying here is that as the limit as x approaches 3 from the right of the function 2x over x minus 3. Okay, so what it's saying is that if x is close to 3 but larger than 3, then the denominator x minus 3 is a small positive number and 2x is close to 6. So the quotient 2x over x minus 3 is a large positive number. Thus, intuitively, we would see that the limit as x approaches 3 from the right would then equal infinity. Okay, and then if we take a look at the next scenario, where we have the limit as x approaches 3 from the left of 2x over x minus 3. Likewise, in this scenario, if x is as close to 3 but smaller than 3, then the denominator x minus 3 is a small negative number, but 2x in the numerator is still a positive number, which is close to 6. So 2x over x minus 3 is a numerically large negative number, and so therefore this would be approaching negative infinity. So the graph of the curve is the following. So let's take a look at the curve here. Okay, so you can see here as x is approaching 3 from the right, okay, it's approaching from the right here, positive infinity. And as it's approaching 3 from the left, it's going towards negative infinity. Now there are two familiar functions whose graphs have vertical asymptotes, which are y equals a natural log of x and y equals a tangent of x. Okay, so from the figure that you can see here on your left, which is figure 6, we can see that the limit as x approaches 0 from the right, okay, so as this function is approaching negative infinity. So you can see here as it's going from the right, it's approaching negative infinity. Now, you can see that the vertical asymptote, and I'm going to abbreviate that as VA, is x is equal to 0. Okay, which is the y-axis. And in fact, the same is true for y is equal to the log of base ax, provided that a is greater than 1. Now, looking at the limit of the tangent as x approaches pi over 2 from the left, okay, you can see that as it's approaching pi over 2 from the left, well, again, what's happening here is that this is where it's approaching from the left and it's going towards positive infinity, which you can see here that the limit as x approaches pi over 2 from the left, the tangent of x, is equal to positive infinity. And let's just go back to that one real quick here. Okay, what can we say is the vertical asymptote? Well, you have vertical asymptotes here the vertical asymptote for this one, for the one that we just looked at, would be x, which is equal to negative pi over 2. And maybe go back to the first question here that we had before here. Okay, what would be the vertical asymptote here? Well, the vertical asymptote would be x is equal to 3. Okay, now let's take a look at example number 2. Okay, in example number 2, okay, what we want to do is we want to be able to find the limit as x approaches 0 of the natural log of the tangent squared x. Okay, so we're going to introduce a new variable, which is t, which is equal to the tangent squared x. So in this example, what we're going to do is we're kind of going to do something like you may have seen in the past as a u substitution. Instead of u substitution, we're going to let t represent the substitution. So in the first step here, we're going to let t equal the tangent squared of x. And then what we're going to do is now we're going to substitute it into our example. So what's going to happen now is that we can see that we're going to let t equal the tangent squared of x. And before we substitute that, let's determine what is happening with t. Okay, so in this scenario, if you have the tangent squared x, which is equal to t. Okay, well, what we do know is that t would have to be greater than or equal to 0. And so by the following, what we can say is that t, which is equal to the tangent squared x, would then be the tangent squared 0, which is equal to 0, as x gets closer to 0, because the tangent is a continuous function. Okay, so what we can say here is that now, by substituting t to be tangent squared of x, we can then write this now as the limit as x approaches 0 of the natural log of t. And that would have to be 0 from the right. And the limit from the right of the natural log from our previous example would be approaching negative infinity. Okay, so if you take a look at the natural log of t here, okay, so imagine that this is the same function, which is a natural log of t. And so from here, what's happening again is that it's approaching 0 from the right, and it's approaching negative infinity. Okay, now let's begin to investigate a behavior of a function defined by f, and that function is x squared minus 1 over x squared plus 1. Okay, so the graph is given here, and you can see that with the graph, okay, this is what's happening. This is our function, which is in blue, which is x squared minus 1 over x squared plus 1. And then now we have a horizontal asymptote at y is equal to 1. So as x grows larger and larger, you can see that the values of the function get closer and closer to 1. So as x is getting larger, well, the value of the function is getting closer and closer to 1. So in fact, it seems that we can make the values of the function as close as we like to 1 by taking x sufficiently large. Now, this situation is expressed by this limit here. The limit as x approaches infinity of x squared minus 1 over x squared plus 1 is equal to 1. Because as x is approaching infinity, as this function keeps going and going and going and going and going, it's not going to touch the horizontal axis, so that means as x is approaching infinity, but it's approaching the value of 1, which gives us our next definition. So if we have a function f be a function defined on some interval from a to infinity, then the limit as x approaches infinity of that function is equal to L, which means the values of the function can be made as close to L as we like by taking x sufficiently large. Now, if you look at these next 3 graphs at the top here, okay, these are geometric illustrations that show that the function is approaching the line y is equal to L in 3 different scenarios. And y is equal to L is called the horizontal asymptote. Now, if you notice that all 3 of these scenarios, okay, as the function, okay, so basically it's saying here as x is approaching positive infinity on this one, you can see that it is approaching y is equal to L. Same thing over here, as x is approaching positive infinity, the function is approaching y is equal to L. And likewise in the third scenario, as x is approaching infinity, okay, the line again is approaching y is equal to L. Now the line y equals L is called a horizontal asymptote of the curve, and y is equal to f of x if either the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x is equal to L. Now, the first scenario represents the 3 graphs above, because as x is approaching positive infinity, that means it's approaching L. Now, if we take a look at the last 2 graphs here, okay, this would say that the function, okay, as x is approaching negative infinity, is approaching y is equal to L. Same thing over here. As this function goes from x to negative infinity, it's approaching the line y is equal to L. Now, if we take a look at the curve, okay, of this function that's sketched in this figure, okay, it has both or 2 horizontal asymptotes. One is at y is equal to 2, and the other one is at y is equal to negative 1. Now, if you notice here that as the limit as x approaches positive infinity, meaning that as x approaches positive infinity, well, this function is approaching y equals negative 1. Now, over here, as the limit of the function as x is approaching negative infinity, that means the graph is approaching 2. Now, for example number 3, we're discussing infinite limits and asymptotes from a graph. And we want to be able to find the infinite limits, the limits at infinity, and the asymptotes for the function of f whose graph is shown in the figure. Okay, so let's take a look at our first scenario here. Okay, so let's start on the left. Now we can see here that this function on the left side, okay, is approaching this direction and then that direction, okay? And that value is at negative 1. So we can say that as the limit as x approaches negative 1 of the function, okay, on the left and on the right side, okay, that means it's approaching positive infinity. Okay, now let's see what happens when it's approaching 2 from the left and from the right. Okay, so as the limit as x is approaching 2 from the left of this function. Okay, so as it's approaching 2 from the left, okay, we can see that it's going towards negative infinity. And as the limit, as x is approaching 2 from the right of this function, is equal to infinity. Thus, both of the lines x equals -1 and x equals 2 are vertical asymptotes. So we can say that x equals -1 and 2 are vertical asymptotes. Okay, now as x becomes large, it appears that f of x approaches 4. But as x decreases through negative values, f of x approaches 2. So let's take a look at that scenario. So now, if we take the limit as x approaches positive infinity of this function, okay, so as x is approaching positive infinity, okay, this function is approaching what value? Well, it's approaching 4. And if we take the limit as now x is approaching negative infinity, so as it's going in this direction, okay, this function is approaching 2. So that means we have two horizontal asymptotes, and the two horizontal asymptotes are at 2 and 4. And those are the horizontal asymptotes. All right, let's take a look at example number 4. Okay, we want to be able to find the limit as x approaches infinity of 1 over x, and the limit as x approaches negative infinity of 1 over x. So I'm going to go ahead and pull up that graph here. Okay, so if you take a look at this function, okay, what is happening here? Well, we can see here that from the graph, okay, the limit as x is approaching positive infinity of the function 1 over x. And let's take a look at this graph here, okay? So as x is approaching positive infinity, the function is approaching what? It's approaching 0. And as the limit of x, which is approaching negative infinity, of 1 over x. So here, as it's approaching negative infinity, the function is approaching what number again? Well, it's approaching 0. Okay, so what this does is this is going to give us our next important definition about 1 over x. Okay, so our next definition states the following, that if n is a positive integer, then whenever you have the limit as x approaches infinity of 1 over x to any power of n, it's going to equal 0. And likewise, if you take the limit as x approaches negative infinity of 1 over x to the n, and again, n being any number, is going to equal 0. Okay, now let's take a look at example number 5. Okay, and this is a quotient of functions that become large. Okay, now as this example, we have the limit as x approaches infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Okay, now our goal, okay, is to rewrite this function so that all of these terms could possibly look like the previous definition. Because once we get this definition, then we can apply the definition to the problem. Okay, so we're going to have to use some algebra tools here. So what we can do, okay, with both the numerator and denominator is multiply both the numerator and denominator by 1 over x squared. Okay, because it's the same thing as multiplying it by 1. So let's see what happens when we multiply it by 1 over x squared. So now we have the limit as x is approaching positive infinity. So 1 over x squared times 3x squared is going to leave you with 3. Minus 1 over x squared times x is going to be 1 over x. And then 1 over x squared times minus 2 is going to give you minus 2 over x squared. In a denominator, 5x squared times 1 over x squared is going to give you the value of 5. 4x squared times 1 over x squared is going to give you plus 4 over x. And then 1 times 1 over x squared is going to give you plus 1 over x squared. Okay, so now we're going to just follow our rules of our quotient. So we're going to take the limit as x approaches infinity of the numerator, which is 3 minus 1 over x minus 2 over x squared, all over the limit as x approaches infinity of 5 plus 4 over x plus 1 over x squared. Okay, now we're going to apply again our limit rules. So now this becomes the limit as x approaches infinity 3 minus the limit as x approaches infinity of 1 over x minus the limit as x approaches infinity of 2 over x squared. And then we're going to divide that by the limit as x approaches infinity of 5 plus the limit as x approaches infinity of 4 over x plus the limit as x approaches infinity of 1 over x squared. Okay, now we can evaluate the limits. Okay, so what happens when we evaluate these limits? Well, when we evaluate these limits, the limit as x approaches infinity of 3 is a constant, so this is 3. Minus, from the previous definition, whenever you have the limit as x approaches infinity of 1 over x, this is going to be 0. Minus the limit as x approaches infinity of 2 over x squared, which is also going to be 0. Divided by the limit as x approaches infinity of a constant, which is 5. The limit as x approaches infinity of 4 over x, that's going to be 0. And then the limit as x approaches infinity of 1 over x squared is going to be 0. So the answer is going to be 3/15. fifths. Okay? So if we take a look at this graph, okay, this is what's happening. So as x is approaching, okay, positive infinity, well, it's approaching the limit of y is equal to 0.6, which is the same thing as 3/5. Okay, let's take a look at example number 6. Okay, number 6, we want to be able to find a difference of functions that become large. We want to compute the limit as x approaches infinity of the square root of x squared plus 1 minus x. Okay, so the first step here is we're going to write down the function again. So this is the limit as x approaches infinity of the function square root of x squared plus 1 minus x. Okay, now what I want to do is I want to go ahead and write this over 1. And the reason why is because, again, using some of your algebra tools, in order to simplify this to be able to go a little further, you want to use rationalizing the numerator. And by rationalizing the numerator, we need to multiply the numerator and denominator by the conjugate, which is the square root of x squared plus 1 plus x all over the square root of x squared plus 1 plus x. Okay, so now let's go ahead and then multiply. Now when we multiply the numerator, we will see that this represents difference of squares. So what's left when you multiply those two together is going to be x squared plus 1, and that's going to be minus x squared. Okay, and that's going to be over the denominator of the square root of x squared plus 1 plus x. Okay, now we can see that when we combine like terms in our numerator, we end up with the limit as x approaches infinity of 1 over the square root of x squared plus 1 plus x. Okay, now we'll be able to see here what's happening with this graph. Okay, but what we can do is we can also use a what here? We can use possibly the squeeze theorem. Okay, so what do we know? Well, we know that this limit as x approaches infinity of 1 over the square root of x squared plus 1 plus x, okay, are in between two numbers. Well, we know it's got to be in between 0, okay, and the limit as x approaches infinity of 1 over x. Well, what we know is that the limit as x approaches infinity of 1 over x, by definition, and what we saw in the previous slides, is equal to 0. So that means that this limit, okay, actually, according to the intermediate value theorem, that 0 is in between there. So then we can conclude that the limit as x approaches infinity of the following function, 1 over the square root of x squared plus 1 plus x would then equal 0. And now we can verify that by looking at its graph. Okay, so here, as x is approaching positive infinity, well, where's the function approaching? Well, it's approaching the value of 0. Okay, let's take a look at example number 7. Okay, now the graph of the natural exponential function y is equal to e to the x has the line y equals 0, the x-axis, as a horizontal asymptote. So the same is true for any exponential function with base a greater than 1. So if you take a look at the figure 16, the corresponding table of values, okay, as the limit as x is approaching negative infinity, so as x is approaching negative infinity, the function is approaching what? 0. Okay? So let's take a look at example number 7. Okay, so we want to be able to evaluate the limit as x approaches 0 from the left of e to the 1 over x. Okay, so again, let's take a look and use our substitution. So the first thing we want to do is we're going to let t equal 1 over x. And so now we can say that the limit as x approaches 0 from the left of t, meaning, okay, what is the graph of 1 over x? Right? Well, we know that the graph of 1 over x looks like the following. We know it's the reciprocal function. So as it is approaching 0 from the left, we can see that it's approaching negative infinity. Again, of the function 1 over x, which we called t. Now, what we can do now is now find the limit. Okay, now that we substituted t, now t is now going to be our value that we're approaching. And that t is going to approach what we got from the previous example, which is negative infinity. So as t approaches negative infinity of the function e to the t. So now let's take a look at what that graph looks like. Well, we know what the exponential function looks like for e of t, right? We know that it is a function that looks like that. So as t is approaching negative infinity, so that means that as it's going towards negative infinity, the function e of t is going to be approaching 0. Okay, let's take a look at example number 8. So for example number 8, we want to be able to find the limit as x approaches infinity of the sine of x. Okay, so remember what the graph of the sine of x looks like. Okay, we're going to draw sort of a random looking figure here. So it starts at 0, and down, back up, and then down and so forth, right? Okay, so as x approaches infinity, okay, what can we say does it approach? Well, in this scenario here, as x increases, the values of sine of x are going to oscillate between 1 and -1 infinitely often. Therefore, if it does that, then it does not exist. So we would say that the limit as x approaches infinity of the sine of x does not exist. Okay, now let's take a look at some infinite limits at infinity, the notation. So the limit as x approaches f of x is equal to infinity is used to indicate that the values of the function become large as x becomes large. So similar meanings are attached to the following symbols, which is what we've seen. Okay, so if you take a look at figures 16 and 17 here, which are these functions here, right? The limit of this function as x is approaching positive infinity is going towards positive infinity. For the cubic function, the limit as x is approaching positive infinity, again, is approaching infinity. Okay, and the limit of the cubic function as x is approaching negative infinity, well, this is approaching negative infinity. Okay, now if we look at this figure now, this demonstrates y is equal to e to the x becomes large as x is approaching infinity at a much faster rate than the cubic function y is equal to x cubed. Okay, so we want to be able to find an infinite limit at infinity. We want to be able to find the limit as x is approaching infinity of x squared minus x. Okay, now if you wrote the following, the limit as x approaches infinity of x squared minus x equal to the limit as x is approaching infinity of x squared minus the limit as x is approaching infinity of x. Okay, you would say that this is infinity minus infinity. Okay, now the limit laws can't be applied to infinite limits because infinity is not a number. Okay, so we can't do it this way. Okay, but we can do it another way. We can say the following. We can say that the limit as x is approaching infinity of x squared minus x, we can factor out an x. So we can say that the limit as x approaches infinity of x times x minus 1 would then equal positive infinity, because both x and x minus 1 become arbitrarily large. Okay, now in example number 10, we want to be able to find the limit as x approaches infinity of x squared plus x over 3 minus x. Okay, so what we're going to do is we're going to take the limit as x approaches infinity of this function Okay, so what we want to do is something similar in a previous example. We're going to divide the numerator and denominator by x, which is the highest power of x that occurs in the denominator. So in the denominator, the highest power of x is x. So we're going to multiply the numerator and the denominator by 1 over x. Now, when we multiply that through, we get the limit as x approaches infinity of x plus 1 all over 3 over x minus 1. So, if we go ahead and rewrite this as the limit as x approaches infinity of x plus 1 all over the limit as x approaches infinity of 3 over x minus 1. Well, as the limit as x approaches infinity of x plus 1, well, that is approaching infinity. Okay, and in the denominator, the limit as x approaches infinity would then be 0 minus 1, which is negative 1, which then would just be negative infinity. So the answer would be negative infinity.